Thank you, Steve, and thank you everyone for inviting me this afternoon. So I think according to the Microsoft classification of cloud users, we are tire kickers, and we're just starting our use of cloud computing. So my role in Newcastle is to work in the Digital Institute with Paul Watson, some of you may know, as a professor of visualization, and so I'm a visualization scientist, researcher. We're trying to use cloud computing to generate new ways of drawing pictures. And the work I'm doing today is supported by two of our research software engineers, Steve Dowsland and Mark Turner, who build the cloud systems for us, and Manu Anthony, who is a Siemens doctoral student working on the visualization side of things. I've not got a lot of time to justify the approach we're taking. If you want to know more, there's a paper Paul and I wrote a couple of years ago which does this. But our interest in looking at the visualization pipeline is in mapping it onto the cloud and where you put different parts of the visualization process. And in the systems I'll show you today, we've put almost all of the visualization process in the cloud itself. And the only thing we're sending to end users on thin clients are pixels and bringing back interaction events of various types depending on the type of visualization we're doing. I'm not going to show any real-time rendering today, but we do have a separate project on that as well. Some of the benefits of this is we're able to use much more powerful graphics engines in the cloud than we could on desktop systems, give a much more rich visualization experience to people on thin clients. We can share large rendering resources between different client users. And what we're hoping particularly is that we can have scalable visualization capacity for big data challenges. And one of the justifications I often give for visualization is that there's a lot of big data in the world. Computers are very good at big data. People are not good at all at big data. Give people more than 3 or 4 things at a time and they get confused. And visualization matches the big data side of things to the big thinking part that people are good at doing. The particular data set I'll talk to you today about is the Newcastle Urban Observatory. This is a set of sensors funded by the UCRIT project, largely across Newcastle and the northeast. It extends quite a long way north and south of Newcastle. Monitoring in real time a whole range of measures about Newcastle, mostly environmental, so temperature, air quality, humidity, sound levels, various things like that. Some also people counting sensors. It generates about 2.5 gigabytes of readings a day, and in total it now has about 650 million readings over the last 3 years. And it's probably the largest open data set from a smart city in the world. There are many people measuring, but very few with an open data set. You can go to this web page, download any part of the data set you like and work with it. A year or so ago now, we started rendering this in the cloud, and we have a set of live renderings running continuously from a small area near our offices, actually our old offices, we've just moved office. Taking a live feed from the Urban Observatory, sending the data out to cloud servers, most often in the USA or sometimes in our private cloud in Newcastle as well, and then sending back the images to our web pages. This is hosted on Azure, and this at the moment has a private cloud backend, which causes us a number of issues. The private cloud part causes a number of issues. More recently, we've updated this. We now have a 3D model of quite a large area of the city, but we use about a kilometre square area, and we put the same sense data into it, and again, we update this in real time. And I'll try. Okay, that appears on that screen and not this one. I'll try and show you that running live. So these are live image feeds from the sensors via the cloud, visualizing, in this case, temperature at a range of different types of rendering. This is for an HD display. We have 4K display, stereo 3D TV. Anyone who's still got a stereo 3D TV, we can feed that direct from here. And there's a 360 visualization which you can put into your Google Daydream headset or other headset and look around in 3D. This is the 2D version of that. We'll zoom into the top of St James's Park. We don't sense if there's a football match happening, which is probably a good thing for Newcastle. But you can see the sensors down St James's Boulevard. There should be a set over on the right as well, but the network that's supporting those at the moment is down. So these images are updated as often as we can. Some of them are updated every minute or so. This one's updated every couple of hours. and gives a idea is it gives a high quality rendering to anyone who's interested in looking at them. We also do a bunch of stuff which isn't part of this talk on Power BI and Tableau teaching for the more routine visualization. This is our research collection. Okay, I'm going to find my way back to PowerPoint. So that's the things we've done in the past. And so one of the things we're now looking at is how we draw much bigger pictures of the data and Newcastle so that we can give a scalable image, which allows us to scale not just through the image, but also into very detailed data sets which we're collecting about individual buildings. And so we have this Terascope project running now, which again aims to allow thin clients to see high quality, large scale visualizations of descriptive statistics coming back from our IoT sensors around the city. It's going to support from city scale to room scale. I hope I'll be able to show you that. And our goal with this, actually I was just talking to Mike, we might be able to get more nodes than I thought. We might be able to update it much more than once a day. But our first goal is to update this image at least once a day. So, to give you an idea of the computational size of this, 1 trillion pixels is 1 million pixels and a bit. And we want to draw that as a single image. And that's equivalent to 530,000 full HD TV images. So I think that's about an hour and a half of HD TV at full resolution. And that'll allow us to zoom in from this size right down to the office. I'll show you on the next couple of slides. About a space about 2.5 meters by 1.25 meters. 1 pixel in the image will be about 1.2 by 1.2 millimeters in the real world. So on the right size display, you'll be able to see the real world almost 1-to-1 scale. The computation itself, we need to compute nearly 66,000 4,000 by 4,000 pixel images, which will be tiled into 5.5 million 512 by 512 images. And that allows us to build an image hierarchy, which will allow the browser, which I'll send around in a minute, to zoom through this image hierarchy in a very liquid and real-time way. And this is the hierarchy that we'll need to compute. At the very lowest level, there's a single 512 tile. The very highest level is about 424,200,000 512 tiles. We've built the architecture, and we've been testing it over Christmas, and this is what we've built. We've done a couple of goes at this, but the current one, we have an Azure Batch Task Queue Management System connected to 128 GPU nodes. I think we now can get a lot more, so that's good. We'll ask for some more when we get back. Feeding out the 5.5 million images into Azure Blob Store, which supports a tool called KRPano, and that's the tool that lets you zoom interactively into the image on any web browser. This system will have a peak of about 372 single precision teraflops. If we'd asked for the next node level up, that would be nearly a petaflop, but we're just testing it out at the moment in a tire-kicking way. It's a 6-core node with 1 Tesla K80 GPU, or 1/2 of 1 K80 GPU in fact, but we don't use the CPU cores almost at all. Almost all the computation we're doing is flat out on the GPU. And that feeds into a terabyte of the blob storage. So this 5.5 million images will use about a terabyte of blob store. Okay, so that's the computation and the architecture. Where are we in progress? Luckily, on Friday, we got some numbers in for my talk. And we started off by rendering a gigapixel image. So that's a 1,000 million pixel image, requiring only 257 4K by 4K images. So that's up to level 8 in this image hierarchy. And I will switch this on and send it around so you can see it. So this is the image. You can zoom in, normal pinch and squeeze stuff, and zoom around and look at what's there. Please do send it back to me at the end of the session. And on this image, we can't zoom into a desk size. We can zoom into a size about a house, but it gives us a startup computation to test out the cloud. And these are our initial results. So we started from 1 node up to 128 nodes. The nice orange line is the ideal scalability. And we're seeing fairly close to ideal, up to about 64 nodes. There's a bit of a glitch at 80 nodes that I'll come back to. 96 nodes actually goes quite fast. And above that, we start to run out of tasks. We've got 128 nodes, only 257 tasks. So about the point where we get less than 3 tasks per node, our scalability is dropping off, not unexpectedly. This bottom graph, you'd expect to see the task time staying constant with number of nodes, but it actually grows slightly. And worryingly, quite a lot at 80 in this first set of results we collected. It may be that these images were firing at the blob store or slowing it down. It may be some other things in the architecture, and they're things we'll have to dig into and look at over time. So we certainly don't want to spend a lot of money on getting many more nodes to find that they're not adding to our speed up and that they're increasing task times. We did investigate the 80 nodes over the weekend, and if we do a number of runs on it, we're actually getting quite variable run times between about 25% different. So this would pull, on average, this onto quite a nice smooth scalability curve. Still dropping off, but not quite as spiky as that. For us, the nice thing about this is that we're getting a machine hardware set worth about £625,000. And for all of these runs we've done, the total cost is about £2,000. So as scientists, we're getting access to a machine we couldn't ever in any other way have got hold of without writing a very large GPSRC grant. It gives us this nice ability to deploy supercomputers on demand. There's only one more slide. So this is the gigapixel image. And I was talking about data at different scales. So this is the 1.2 roughly kilometre square region of the city. This is our new computer science building in Newcastle we moved into last September. And there's about 900 sensors in there, readings anything from a few minutes to a tenth to 10 milliseconds for the electricity power sensors, which we're going to have to find some way to visualize. This is one floor with my office on it. And on the office scale data size, the top left, that's Paul Watson's office, if you know Paul. That's a temperature sensor in his office, which also measures CO2 levels, so we can tell how much he's talking, and whether he's in his office or not, which starts to bring us some ethical questions about whether or not we should present all the data we know about the building. If I click on this, this is the image being served from the Azure Blob server in the US East Coast servers. And we can zoom in to about building level. The sensor sizes will change. Should be able to zoom right into office level, nearly. Okay, so this is a gigapixel image. Once we've got the terapixel image, we should be able to keep going down to a region about the size of a desk. And then represent multiple sensors in small offices and areas. So far, I want to switch that off. Things are going reasonably well. The scaling's looking quite good. This is working quite well. Assuming all the terapixel scaling works and we can create an efficient supercomputer on demand for visualization, then the types of things that we're looking at doing are these two things here. It's becoming clear that big data is too difficult for visualization scientists to draw pictures of. They can't get their heads around it or lay it out well. So we're going to try and build a series of AI-based optimization techniques where we generate hundreds or possibly thousands of pictures and use an optimization function, a cost function, to choose the best one for your human visual system. So we're building some simple models of the human visual system to help do that, which will require in the background a very large supercomputing system to generate images. We'd also like to generate cinema quality interactive films, so you can kind of fly around these spaces at a quality beyond that which you'll get from a desktop computer. Okay, that's me done.